When the intermolecular hydrogen bonding will form, it will be having higher boiling point. The solubility decreases with increase in size of the hydrophobic group. Phenol is slightly acidic in nature. It dissociates partially in water to give phenoxide ion and a proton. Substituent is electron donating group which is attached to the phenol. What will be the effect for acidity? Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now, I am going to start session 4 from the chapter Alcohols, Phenols and Ethers. In the previous session, we have discussed about reactions involving cleavage bond of carbon and oxygen bond in alcohols, identification of primary, secondary and tertiary alcohols, properties of methanol and about phenols, classification of phenols, nomenclature of phenols and preparation of phenols. These are the contents already we have discussed in the previous session. In the current session, we will discuss about physical and chemical properties of phenols. Okay. Physical properties of phenols. Phenols consist of two parts, an aryl group and one hydroxyl group. The properties of phenols are due to the hydroxyl group. Due to the functional group of phenol, that is OH, which is a hydroxyl group, the properties of phenols will always completely depend on the functional group. First one, boiling point. In phenols, the hydrogen atom of hydroxyl group is bonded to an electronegative oxygen atom. Therefore, it is capable of forming intermolecular hydrogen bonding. In phenols, hydroxyl group is present. In that hydroxyl group, it is completely bonded to electronegative oxygen atom. So, there is a chance or there is a capable of forming intermolecular hydrogen bonding. Okay. See here, molecular hydrogen bonding can be easily formed. Hence, phenols have higher boiling points than the corresponding other classes compounds, namely hydrocarbons, ethers and haloalkanes or haloarenes of comparable molecular masses. Once again, due to the hydrogen bond of OH group is bonded with electronegative atom, that is oxygen. Therefore, it is capable of formation of intermolecular hydrogen bonding. When the intermolecular hydrogen bonding will form, it will be having higher boiling point. So, phenols are having higher boiling point comparative to hydrocarbons, haloalkanes, haloarenes and ethers, etc. Next, solubility. The solubility of phenols in water is due to their ability to form hydrogen bonds with water molecules. The solubility decreases with increase in size of the hydrophobic group. Okay. The solubility of phenols in water is due to the formation of hydrogen bonds with water molecules. The solubility will decrease when size of hydrophobic means water repellent groups will form, and when the size of water repellent group will be increased, obviously solubility will decrease. Okay, but here solubility will be done very nicely because of formation of hydrogen bonding. Okay. Next, chemical properties of phenols. The chemical properties of phenols are mainly due to the presence of hydroxyl functional group. Always the compound will be dependent on its functional group. Like that, phenols are completely dependent on hydroxyl group, which is a functional group of that compound. The presence of aromatic benzene ring provides some characteristic chemical reactions for phenols. The reactions of phenols group in hydroxyl group in phenols may be divided into two classes, that is reaction involving cleavage of oxygen hydrogen bond and reaction involving in cleavage of carbon and oxygen bond. There is two reactions should happen involving cleavage of oxygen and hydrogen bond and reaction involving cleavage of carbon and oxygen bond. So, reactions involving cleavage of oxygen and hydrogen bond. First one, acidity of phenols, reaction with metals. Acidity of phenols will be seen through the reaction with metals. Phenols react with highly electropositive alkali metals such as sodium, potassium, etc. to yield corresponding alkoxide with liberation of hydrogen gas. Phenols will react with electropositive metals and it will form alkoxides with the liberation of hydrogen gas. Here we will see phenol is reacting with electropositive metal like sodium, and it will form sodium phenate, which is an alkoxide with the liberation of hydrogen gas. Reaction with alkali. Phenols react with aqueous sodium hydroxide to form sodium phenoxide, but alcohols are neutral to this reaction. Phenols will also react with base, which is a sodium hydroxide, and it will form sodium phenoxide here, okay, that is sodium phenate with the liberation of water. But this kind of reaction cannot be seen through alcohols. The above reactions show that phenols are acidic in nature. In fact, phenols are bronze-state acids, that is, they can donate a proton to a strong base. The above reaction we can prove that phenols are acidic in nature because they are donating one proton, and it will be acting as bronze-state acids because they can donate a proton to a strong base. Acidity of phenols. Phenol is slightly acidic in nature. It dissociates partially in water to give phenoxide ion and a proton. Phenol will get partially dissociate in water and it will form phenoxide ion plus proton. Okay. Here it will get partially dissociate. So, it is slightly acidic in nature. Both phenol and phenoxide ion are stabilized by the following resonance structure. Okay. This is resonating structure of phenol. Oxygen is electronegative in nature. So, donating electrons for the conjugation, and here it will keeps on moving for the phenol molecule. This is phenoxide ion. Here also more electrons are involved and it will enter into the conjugation. See here, it is the actual structure of phenoxide ion. Here hydrogen you cannot expect. Effect of substituent on acidity of phenol. When the substituents are present, what will be the effect of acidity of phenol? We will see now. Effect of electron donating group on acidity of phenol. If the substituent is electron donating group which is attached to the phenol, what will be the effect for acidity? Okay. Electron donating groups like methyl group increases the electron density on oxygen of phenoxide ion and the stability of phenoxide ion decreases. Hence, acidic strength decreases, therefore cresols are less acidic than phenol. When electron donating group like methyl, when it has been attached to the phenoxide ion, its electron density will increases and stability of phenoxide ion will decrease. Then what will happen? Hence, acidic strength will also decreases. Okay. Therefore, cresols are less acidic than phenols. Next, effect of electron withdrawing groups on the acidity of phenols. Now we have seen with respect to electron donating group. Now we have seen electron donating group. Now we will see with the effect of electron withdrawing group. Electron withdrawing groups like nitro group decreases the electron density on the oxygen of phenoxide ion and the stability of phenoxide ion will increases. When the electron withdrawing group is there, electron density will decreases regarding to oxygen of phenoxide ion, but the stability of phenoxide ion will get increased. Hence, acidic strength increases, therefore nitrophenols are more acidic than phenols. Okay, acidity, when acidity are increased, when the electron withdrawing group substituent will be attached for the phenols. This effect is more pronounced when such a group is present at ortho and para position. When this electron withdrawing group is attached at ortho and para position, that effect of acidity increasing will be seen more. It is due to the effective delocalization of negative charge in phenoxide ion. As the number of nitro groups increases on phenol, acidic strength of phenol will increases. As I told already, when electron withdrawing group substituent will be attached to the phenol, acidic strength of phenols will increase, and that too in ortho and para positions. Okay. Next, esterification of phenols. Esters are produced when phenols are heated with carboxylic acids in the presence of an acid catalyst. This reaction is called esterification. The catalyst is usually concentrated sulfuric acid or dry HCl. The function of concentrated sulfuric acid is acting as protonating agent or dehydrating agent. Protonating agent means donation of proton can be expected from the acid, or dehydrating agent means the removal of water molecule can be expected from the action of acids. The reaction is reversible and the equilibrium can be shifted towards the forward direction by removing water as soon as it is forward. And this reaction could be reversible by removal of water. Okay. When phenol is reacted with carboxylic acid, in the presence of acid, it will form ester by the removal of water. How it can be reversible? When the removal of water, if added to again ester, it will form phenol and carboxylic acids. Here the acid will donate proton as a protonating agent and remove the water molecule as dehydrating agent. We will see one example. Benzoic acid, when reacted with phenol, it forms phenyl benzoate, which is a ester with the removal of water. This is called esterification of phenols. Next, acylation of phenols. Esters can also be obtained by treating phenols with acid chlorides or acid anhydrides. This reaction with acid chloride is carried out in the presence of pyridine base so as to neutralize HCl, which is formed during the reaction. When phenol react with acid chloride or acid anhydride in the presence of pyridine, which is a base, it will form its ester and the byproduct of hydrochloric acid. Here, phenol, when it is reacting with ethyl acid chloride in the presence of pyridine, phenyl acetate will form. Acetylation can also be done by treating phenol with acidic anhydride in the presence of concentrated sulfuric acid. We have told acylation of phenols can be done by acid chloride or acid anhydride. Before we have seen through acid chloride, now with acid anhydride. Salicylic acid, which is a carboxylic acid, treated with acetic anhydride, it will form aspirin and acetic acid in the presence of concentrated sulfuric acid. Next, electrophilic substitution reaction of phenol. Phenol is more reactive towards electrophilic substitution reactions than benzene. Since they are more reactive, they will involve in electrophilic substitution reaction than benzene. This is because of hydroxyl group, which increases electron density in benzene ring by donating the lone pair of electrons on oxygen atom of the hydroxyl group. Moreover, phenol is stabilized by resonance as given below. Okay. Why the phenols will be more reactive towards electrophilic substitution reaction? Because of hydroxyl group, which increases the electron density in benzene and donating the lone pair of electrons on oxygen atom of the hydroxyl group. Due to this electron donating capacity of oxygen, it gets stabilized through resonance. This is the overall resonance effect of phenols. Okay, that is why it is reactive towards electrophilic substitution reaction. It is clear from the above structures, carbon atoms at ortho and para positions acquire negative charge. Ortho and para positions will acquire more negative charge. As a result, electrophiles attack these positions to form ortho and para derivatives. Okay, ortho and para positions will get more negative charge. That's why it will acquire in that position only and it will form ortho para derivatives. Next, nitration. With dilute nitric acid at low temperatures, that is 298 Kelvin, phenol gives a mixture of ortho and para nitrophenols. Okay, when phenol reacting with dilute nitric acid, it will form ortho nitrophenol and para nitrophenol with the removal of water molecule. The ortho and para isomers can be separated by steam distillation. What all the ortho and para structures are being formed from the same reaction, it has to get separated through steam distillation. Ortho nitrophenol is steam volatile due to intramolecular hydrogen bonding, while para nitrophenol is less volatile due to the intermolecular hydrogen bonding. Ortho is intramolecular, means within the molecular the hydrogen bond will form, that's why it is steam volatile and it can be removed easily. But para nitrophenol or intermolecular hydrogen bonding will form, that's why it cannot be easily volatile by steam, which causes the association of molecules. Okay, in ortho nitrophenol intra hydrogen bonding can be seen. In para nitrophenol intermolecular hydrogen bonding can be seen. So here association of molecules are more comparative to ortho nitrophenol. Okay, that's why it can be easily removed by steam distillation. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol, which is a common name picric acid. When phenols treated with nitric acid, it will form 2,4,6-trinitro, because 3 nitro groups are there. Trinitrophenol will form, which is a picric acid as a common name. Industrially, picric acid is prepared by treating phenol first with concentrated H2SO4, which converts it into 2,4-disulfonic acid. This yields picric acid on treating with concentrated nitric acid. Usually in industry, picric acid, how it will be treated? Phenol will treated with sulfuric acid as a 2,4-disulfonic acid. Later it will be reacted with concentrated nitric acid to form 2,4,6-trinitrophenols. Okay. Next, halogenation. In aqueous medium, halogenation takes place at the available ortho and para positions, resulting in a tri-substituted product. Halogenation will form at ortho and para positions and it will produce tri-substituted product. For example, when phenol is treated with bromine water, a white precipitate of 2,4,6-tribromophenol is formed. You see here, phenol reacting with halogen in the presence of water, that is aqueous medium, it will form tri-substituted product, means 2,4,6-tribromophenol can be seen with the removal of hydrogen halide. In aqueous medium, phenol ionizes to give phenate ion. The presence of negative charge on the oxygen atom activates the ring to a large extent towards the electrophilic substitution, resulting in tri-substitution. Usually in aqueous medium, means in the presence of water, phenol ionizes to give phenate ion, but the presence of negative charge on the oxygen atom activates the ring to a large extent and it will form towards the electronegative substitution reaction to form tri-substitution. Okay. In non-polar solvents such as CCl4 or carbon tetrachloride or carbon disulfide solution, the halogenation becomes slow and only one halogen atom is introduced either at the ortho or para position. Thus, a mixture of isomeric product is obtained. Like in polar solvent like water, it will form tri-substituted compound, but in non-polar solvents like carbon tetrachloride or carbon disulfide, it will form only one substituted compounds. Either it will form at ortho position or it will form in para positions. And here isomers could be expected from its product. Okay, phenol reacted with bromine in carbon disulfide solution, which is a non-polar solvent, it will form orthobromophenol and parabromophenol. But orthobromophenol is minor product, parabromophenol is major product with the liberation of halogen bromide. In non-polar solvent, phenate ion is not formed. This means that the activation of the ring gets suppressed since the oxygen has no negative charge on it. Here, ring formation will not get formed, it will be suppressed because of absence of negative charge on the oxygen. As a result, OH group, that is hydroxyl group, donates the electron pair to the ring only a small extent and monosubstitution will take place at ortho or para positions. Next, Kolbe's reaction. On a reaction of sodium salt of phenol with carbon dioxide gas at 413 Kelvin and a pressure of 6 to 7 atmospheres, sodium salicylate is formed, which on acidification yields salicylic acid. This reaction is called Kolbe's reaction. When phenol treated with sodium hydroxide, sodium salt of phenoxide will form. When it has been treated with carbon dioxide at 143 Kelvin and 6 to 7 atmospheric pressure, it will form sodium salicylate, and when get acidified with some acid, it will form salicylic acid, that is 2-hydroxybenzoic acid, that will called Kolbe's reaction, which is very important for your examination purpose. Next, Reimer-Tiemann reaction. This is also very important reaction. When phenol is heated with chloroform in the presence of sodium hydroxide at 340 Kelvin, followed by hydrolysis, orthohydroxybenzaldehyde will form. This reaction is called Reimer-Tiemann reaction. See here, phenol when reacted with chloroform plus aqueous sodium hydroxide solution, it will form an intermediate product, and those intermediate product will be unstable, and further it will reacted with sodium hydroxide and In that, removal of water molecule could be seen, and further it will be acidified with hydrochloric acid. There it will form salicylaldehyde. From phenol, aldehyde can be formed. In the Kolbe's reaction, from phenol, salicylic acid can be formed. Next, reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. Okay, by removal of ZnO, that is zinc oxide, it will form benzene, phenol to benzene. Oxidation of phenol. The oxidation of phenol by chromic acid forms benzoquinone. Quinone are not aromatic compounds, they are alpha beta unsaturated ketones. When phenol treated with oxidizing agent called potassium dichromate or chromic acid, it will form benzoquinone. Those benzoquinone also called as alpha beta unsaturated ketone with zinc oxide. In the presence of air, phenols are slowly oxidized to pink colored mixtures called quinones. Okay. In the presence of air also, it will get oxidized to form benzoquinone, but here in the presence of oxidizing agent, it will get benzoquinone little bit fastly. These are all the chemical properties of phenols. Okay, next we will see uses of phenol. Phenol is used as a powerful antiseptic in soaps and lotions, etc. In the manufacture of bakelite through condensation polymer of phenol and formaldehyde. In the manufacture of Detolls, that is, those are also antiseptics. In the manufacture of pharmaceutical products such as salicylic acid and aspirin, etc. In the manufacture of dyes like phenolphthalein, picric acid, etc. Phenolphthalein, pink colored agent, and picric acid also some yellowish color agent, and which will be used as dyes. These are the uses of phenols, and in the next upcoming session will be discussed as classification of ethers, nomenclature of ethers. Complete about ethers we will discuss in the next session. I hope you have understood completely whatever I have taught in this session. We will be meet in the upcoming session. Till that, thank you.